We all know that when there are 2-point charges separated by a distance d, the magnitude of force of repulsion between them is kq1 q2 by d square according to Coulomb's law. Don't want to go into the details of K and the properties of medium. I want to discuss today a very fundamental question. It's like point charges are a mathematical abstraction. What if instead of point charges we have these spherical shells which have charge q1 and q2 upon them, and their centers are at a distance d? You see, they have some radius r1 and r2. If this r1 tends to 0 and r2 tends to 0, then they will be like point charges, and the force of repulsion between them will be same as this, but not in that approximation when r1 and r2 are not very small as compared to d. So in this kind of situation, you have finite sized spherical shells, so it's not a point charge. So what happens in this case? What do you think about like the force of repulsion? You see here, like some charges are closer. If you still think in terms of point charges, like this is composed of some very small point charge elements, then some elements are closer than d, while some elements are farther than d. And looking at these things, what can you say about the magnitude of force of repulsion here between these two spheres? Would it still be kq1 q2 by d square? The closeness of charges like here and the charges getting farther than d, all this effect will cancel out, and we will still get the force of repulsion to be kq1 q2 by d square, or it would be less than d square, or it will be more than d square. This is a very fundamental question, and this could be ground breaking for a few people. So somebody can say, like, intuitively I feel that this should be equal to kq1 q2 by d square, but then we need to go into it, we need to analyze it. How? We need to reason the more simpler things. Let's go into this. The first thing I want to talk about also in these kind of questions, when you will start calculating the force of repulsion on let's say the second spherical shell by the first spherical shell, you will take an element here, and on this element you will see many forces. You will see some forces by the positively charged, let's say that these charges are positive, so positively charged elements, they are repelling this element here, but the elements on the same spherical shell are also repelling this element. And which force to consider and which force not to consider when we are thinking about the force of repulsion between these spheres? So one thing which we normally miss is that these bodies are rigid bodies, so they also have intermolecular forces or internal forces, because of which this is a solid. So there are those forces on this element also. So on a particular element there are many kind of forces. Which forces should we consider? Well, it might be very natural for some people to understand that we should only consider the forces due to the other sphere. But let me go into it and let me show you a very interesting thing about rigid bodies and why we shouldn't consider those forces in our equation. So suppose this is a charged spherical shell, and then there are these different charged elements here, very small point charge kind of elements, and they are repelling each other. So let's just think about one of the element, and this element is feeling a lot of repulsion from the other elements on this same sphere. But then because of this it should have moved up, but it doesn't go up, it doesn't leave the body, because there are some forces on the surface which is holding it back. So there are these internal forces, surface forces, which balance the electrostatic repulsion on an element. So you see, in more real situation, I can say that suppose this is a sphere which is negatively charged, so that's why you are seeing more electrons than protons. So you take a proton and you see that it is facing a lot of repulsion from electrons, but then at the same time there are also protons here which are attracting it. But then you would say that, that the repulsion is more than the attraction. But then there are some other kind of things which can be here, some other quantum mechanical interactions, like which you can say metallic bonding. And why this solid is holding together, I'm assuming that this is a metal. But if this is some other kind of solid, there will be some other kind of forces, quantum mechanical nature, forces of quantum mechanical nature on the surface, which will be holding that solid together. So these will be adjustable in nature. So if there is more repulsion, the bonding, the chemical forces of quantum mechanical nature there will adjust itself and still hold the solid, right? If it's too much, then maybe the solid can disintegrate, but we are not looking into that case. We are not going in there. Okay, so just to give you a simple example, you can think a rigid body and like this, in which you have separate charge separated here, so you can see discretely, and there are some internal mechanism with which the solid is made. These blue dots, blue lines, these are like maybe rigid rods which are holding these balls together. So when you put charge on these balls, this body will not start to move on its own to some other place, right? It will stay there. Neither it will start to rotate, because when you see all the forces inside this system, you will see, like on this second particle here, you will see these three kinds of electrostatic repulsion, from one in this direction, from 4 in this direction, from Q3 in this direction. And you will also see that there are these tensions in these rods which will be able to balance all these forces. So it would be possible if you do an analysis, and if you make equations for simple situations, you will always be able to figure out solutions. And when the situation gets more complicated, you can leave it to the nature. The nature will adjust the forces in such a way that the body will not move. This is at least what we observe when we do experiments. Okay. So because of internal forces, the system is not going to move. The center of mass of the system is not going to move anywhere. Anyways, so let me show you something very interesting here also. So let's write all the equations here. For the particle 1, we can write 3 electrostatic forces and 3 tensions, because there are 3 rods here coming together. You can pause the video and analyze these equations. And for Q3, 2 tension forces balancing 3 repulsive forces. This. And 4, you can also write this. And look at this, like all the forces. If you sum all the forces, so you will get all the opposite pairs of tension, and you will get all the opposite pairs of these electrostatic repulsion. And these equations are consistent in a way. If you add all these equations, you will get 0 plus 0 is equal to 0. But basically what is happening here, that in case of this rigid body, if there is this electrostatic force here of repulsion, all the electrostatic force of repulsion within the system is going to get cancelled out, and all the internal forces of adjustable nature which is holding the rigid body together will also get cancelled out. So this is why I'm saying, like and also all the elements will have balanced forces. If there is no external field, they are repelling among themselves. All the elements, like this element is having balanced forces, this element is also having balanced forces. All electrostatic forces cancel out, all adjustable forces cancel out. Net torque is also going to be 0. You can take any point and calculate torque from there. That is also going to be 0. So the rigid body will not start to move and rotate because of its own charges. That's the first thing. So, but if it is placed in an external electric field, you will see that these external forces will appear on the system, and the internal forces can now not adjust these forces, because internal forces will be within the system. Suppose on Q2, if there is some extra force Q2E here, and the internal forces, because of increase in tension, it can balance, let's say it can balance Q2E, there will be some extra internal forces, but their opposite pairs will also be there in the system, and then these forces will also be in in the opposite direction. So you see that these internal forces, because their pairs are going to be inside the system, they cannot overcome these forces, and now the body will start to move and rotate in so it depends on where the center of mass is, the rotation, but at least its center of mass will start to accelerate, it will start to move in this direction. So this is why when we are talking about these two spheres and charges on these spherical shells, when you are calculating the repulsive force between these two spherical shells, you need not to consider the internal forces. Like if you take this element here and you're also considering the repulsive forces within the sphere, they will be balanced by the internal forces. So you don't have to worry about that. You just have to think about like how much repulsion each element. You just have to think like how much electrostatic repulsion of all elements. Let's say we are talking about how much repulsion is going to Q2 is going to experience. This spherical shell 2 S2 is going to experience. Then you should take all elements on this S2, and then you should calculate its repulsion from each element in the S1. Let's say this is S1. So you need to think of these forces only. Okay. Also, when you think like when you take this element and you are thinking about how much repulsion it is going to experience from the whole S1, so you, instead of going one by one, you can just think like the electric field due to this spherical shell is same as the electric field due to a point charge centered, the whole charge here on the spherical shell centered at this point. We can easily prove it through Gauss law. So this, I'm not going to go into this. So suppose we know that. So supposing that we know about Gauss law and we know that inside a charged spherical shell, electric field is 0, and outside the electric field is just like if you have, let's say, charge Q here, the radius of the spherical shell doesn't matter at this point, this distance only matters, and it's just like this whole charge on the spherical shell is centered at its center and like a point charge, and the electric field by that point charge will be same as the electric field produced by the spherical shell. So the electric field will be Q by 4 pi epsilon naught R square. You see there is no role of the radius of this spherical shell here, just this small R square. So if we know that, so we can consider that this whole Q1 charge is centered here, and then from here, so we can calculate the force of repulsion on Q2, and it will still be the same. So now we have reached a very interesting point where we have replaced one of the spherical shell with a point charge. Can we do it for the second spherical shell also with the use of reason? Let's think about it. So one more thing, you see that the force of repulsion will not be in this direction, right? The force of repulsion due to symmetry, it should be in the direction of line joining their centers. So force of repulsion will be in this direction, because if you say like if it's in this direction, then I will say like why not in this direction? This direction is also equivalent to this direction. If 1 and 2, they are like same direction as compared in this kind of geometry. So you can't say that it is along 1. If you say it is along 1, I will say that it could be along 2 also. Then not only this 2, there's this whole circular ring you can make here, and all these directions are equivalent. So the only unique direction which we have in which we can have these repulsive force is this one. So that's very simple. Because of symmetry, we can say that the electrostatic force of repulsion is along this direction. So if you calculate force of repulsion on each element, you should take this component only, and you can leave this component. Okay. So, but let's see, like until now we have done this, we have replaced the one of the spherical shells by a point charge, and that we can do. So we are finding the force of repulsion on 2 by 1. So we are focusing like what is the force of repulsion on the sphere 2. You see, these small things are very important. Don't go into circular reasoning. I am making myself very clear here. I am figuring out the force of repulsion on S2 due to S1, and because of that the same kind of fields, I can replace this S1 by a point charge, and then my force of repulsion on S2 will still be the same. So the question is this one: can we also collapse Q2 to a point? If not, if you don't want to collapse Q2 to a point, you can think this S2 as like you can break it down into these small circular ring elements, and from there you can do the integration and figure out the force of repulsion, and then realize whether the formula is same, whether the result is same as kq1 q2 by d square or not. But that's a longer route. There's a beautiful argument involved here, which I will show you first. So let's say that F21 is force on 2 by 1, F12 is force on sphere 1 by 2. So this is S1, this is S2. Okay, so these forces are in these directions also. We have already proved that, because this is the only unique direction in this geometry. And the magnitude of these forces should also be the same because of Newton's third law, right? If you're not convinced about this, give it some time. And then we know that we can collapse one of the sphere. We can while calculating F21, we can collapse this sphere spherical shell to just a point, and from here we can calculate F21. Okay, so our F21 is still going to be the same, but because of Newton's third law, our F12 here, the force of repulsion experienced by this Q1 charge due to this spherical shell, is also going to be the same as this force here. What this spherical shell was observing, the same force is being observed by this point charge here. And because these two forces are same, now we can shift our attention to calculate the you see, F21 has not changed, F12 has not changed as before. They are the same, their magnitudes and direction are the same as before. So now we can shift our attention not from F21 to F12. Instead of trying to figure out F21, now let's think about F12. So F12 will experience a force of repulsion because of this spherical shell, and the electric field of this spherical shell will be same as a point charge which can be placed on its center Q2. And now you see, you're using Newton's third law and shifting your attention from one side to the other, and then you can be completely sure that you can replace both these spherical shells by a point charge as far as calculation of repulsive force is concerned. So the answer would be this one. You can feel that this was very intuitive. I knew you, but you didn't knew unless and until you would have had this kind of very subtle reasoning. I have been a fan of these kind of reasonings from my childhood. Things which can seem to be true, sometimes they turn out to be false. So it's very important to seal them with proper reason. Okay, so now I can show you that if you want to do this integration, like when we had collapsed, when we the Q1, the collapsing of Q1 was very simple. So this Q1 collapsed to the center from here, and if you want to calculate the force of repulsion on experienced by this whole spherical shell, you could consider that there are these circular ring elements, and you can take an element like this at an angle theta, and d theta you can make here, and you can take a circular ring element, and that area would be 2 pi r2 sine theta, because this will be r2 sine theta. So and this width will be r2 d theta. So I think I am not going to explain this. I hope my viewers know about this. So dA is this, and then you can write dq, so the surface charge density into this element, area of this element, and that is like this. And now you see, like, you can think about, like, from this point charge, all the points on this circular ring are at a distance this one, right? And then you can simplify it to this one. So at a very complicated integration will also give you the same result. So I will show you the integration. If you have already understood what I have done, you don't need to see this integration and be happy with it, but still doubt as much as you can. So then you see, like all the points on this ring is at this same distance, at this distance which we are calling small r here, and you can figure it out by Pythagoras theorem. It's not that difficult. So you see that this distance was d, and then there is some r2 cos theta also. So d plus r2 cos theta squared plus r2 sin theta squared. Okay, but the forces are in this direction, but all the forces, yeah, we will have to take this component in this direction only. We already talked about that. So this cos alpha I will have to multiply. So this cos alpha can also be calculated in the right angle triangle. So using that, you can write df. This is the electric field due to this point charge at the location of the ring, and this is the charge on the ring. So you get that f, but you also need to multiply this cos theta factor. So this is the cos theta factor, and have fun integrating this. I had a lot of fun integrating this, and when I came closer and closer to the result, I was very excited, like what is going to happen. So you can do it on yourself, or you can just follow this video. This I have used this substitution here. You can use something else, but if you get stuck, you can watch this solution. I will just move the slides slowly and slowly. You see, this is very interesting. I love these kind of things when things get very complicated and they turn out to give you a very simple result later on. I love these cancellations when they happen later on. So you see, finally I get the same result. So these kind of things I would encourage for people who are doing independent research on their own. They don't follow books. They have heard about some arguments. They have heard about some situations, but when they see something, when they see some logical explanation, they should verify it with 2 or 3 methods, and make to feel that the result is more convincing. Thank you.